So we're going to quickly do a review of electric fields and then electric potential. And then the next video we'll talk a little bit about electric circuits. So here we go. Let's give this a shot. So let's start with electric fields. So big property about electric field lines, they start on positive charges and they end on negative charges. So if you and I were to draw, say, a charge distribution, and we were to draw the electric field, which is a description of the electrical influence, we would expect that lines of electric field are coming out of the positive charge and they're entering the negative charge here. So if I was to fill this diagram with electric field lines, I might expect something like this. I'm using at least one property of electric fields as I complete this picture, and that is that electric field lines never cross. So that's kind of an important property. You'll see that lines of equipotential do the very same thing. Why does an electric field have a direction? Well, the field points in the direction of the force felt on a positive charge. And remember that a negative charge is going to feel a force in precisely the opposite direction. So for a distribution of point charges, there's a formula for the electric field that's coming off of that point charge. You'll remember that E, the strength of the electric field, is equal to KQ divided by R squared, and that squared's important. Distinguishes it from electrical potential. Suppose I have lots of charges, like a big distribution here, and I want to find the electric field, say, at this point. Well, what I would do is I would calculate the field from each of these individual charges, and I would add them together in a special way that takes the direction of those electric fields into account, vector addition. We say that E, the total field or the net field, is equal to the vector sum of the individual fields. That's just to say that we recognize that direction is important. So for example, we could say, okay, let's say at point A I have a field that's pointing this way from some source that's 5 newtons per coulomb. And at the same point, there's another source of field which at this point gives maybe, I don't know, a 2 newton per coulomb field. And I want to find the net field. Well, what we would do is we would add these together in a way that takes direction into account. And we wouldn't just add 5 to 2. We would subtract the 2 because they're pointed in different directions. So we would say that the total field be pointed in this direction, and it would be 3 newtons per coulomb. This is the total field. And that is all we're talking about when we use this crazy notation up here, the vector summation, just so you're kind of aware. So we do add fields as if they were vectors. Okay. So you'll remember that we couched this discussion of electric fields in terms of charges. So empirically, we know that positive charges and negative charges attract each other, and that like charges repel. And this has to do with forces, not necessarily with fields, although we do have an interpretation of this in terms of fields, right? So you remember that the forces felt between two charges, the electrical force was equal to K, the strength of the first charge times the strength of the second charge divided by their separation squared. That was the force felt between two charges. In general, the force that you feel is equal to your charge times the strength of the electric field that's around you. So notice that if Q is 0, say you're a neutron, you don't feel any charge, you don't feel any force, no matter how strong the electric field is. This could be a bajillion newtons per coulomb for all we know, right? And a neutron would feel nothing. Okay, so this is kind of how we described electric fields. We had a little formula for estimating the strength of the electric field that comes off of each point charge. And we had a way of adding those contributions together. We had to make sure that we understood the principle that positive charges emanate electric field lines and negative charges cause them collect electric field lines. And then we added those fields together in vector format. Okay, all right. So much for electric fields. So let's try to put this together in something of a coherent way here with voltage. So electric fields are one way to describe how a charge over here sees a charge over there and feels an influence from him. The other perspective is thinking about voltage. So let's say I have positive charges collected over here somewhere, and I have negative charges collected over here, and I have a positive charge in the middle. I know that that positive charge is going to be repulsed by the other positive charges and attracted by the negative charges and want to go in this direction. What voltage does is it kind of interprets this in terms of a landscape. We have a mountain over here, and here's the positive charge, and a valley over here. This mountain's caused by positive charge, and this valley is caused by negative charge. And all this positive charge wants to do in this interpretation is roll down this landscape. And so voltage is kind of an easier concept in many ways to picture than electric field lines, although there is a very tight connection between the two. So what we're going to do is I'm just going to draw a little example here. Let's say I have a 200 volt contour line. Remember, we always draw contour plots. We do voltages here. I'm going to say that's the 0 volt line, and I'm actually going to put a pit over here. This will be the negative 100 volt line. Maybe there's a negative 200 volt line here. So this is a contour representation. This is a relative mountain, a positive charge, and here's a valley over here if you're picturing that. So if I have a positive charge in this potential, the way that it's going to roll, it's going to try to roll off this mountain and into that pit. So it's going to move sort of to the lower right hand corner of the screen there. So if we're talking about landscapes, the reason why we do that is so that we can speak about energies. So if I have a landscape here, and this was a ball going on this landscape, then potential energy would be mgh. But this is not a normal landscape, it's voltage, and so we have a slightly different definition of potential energy. It's the charge in question times the potential, or the voltage here. So this is the electrical potential, or just what the voltage is. And so this is our new mgh, if you like. It's the way we describe that. So this can be exchanged for kinetic energy. If you lose potential energy, you gain kinetic energy. We keep the sign on the potential, and we keep the sign on the charge. So an electron would have a negative charge in this case. And so this is important because electrons are going to preferentially want to roll uphill. They roll in the opposite direction as positive charge. So the analogy sort of breaks down in that particular sense. But we had to choose something as positive and something as negative. So I suppose it was a little bit inevitable. But if we keep track of the signs in this equation, those types of issues will work themselves out. We don't need to be keeping track of electron rolling uphill. We just keep using the signs for the potential. Okay, all right. So there is a connection between the electric fields, between E fields and potential, aka voltage. And that potential is just this. It's that the electric field, or the strength of the electric field, is equal to the change in voltage divided by the change in position. That's just a fancy mathematical way of saying that E is the slope of V, which is a powerful idea. So just to kind of unpack that a little bit, if E is the strongest or biggest when the voltage changes rapidly with distance, or with position, I should say, maybe. Again, that's just a fancy way of saying it's strongest when, or I should say where, the potential is steepest, again, aka where contour lines are closest together. So let me just draw an example here, just really quick, so that you can kind of picture what I'm saying. So again, I'm going to have a couple of I don't know. So we have a mountain up here and a valley down here, maybe. And I have point A, point B, and maybe point C. I don't know. And the question is where would the electric field be the strongest? Where I'm going to look is where the landscape is the steepest. And that's where the contour lines are going to be closest together. So B is where the voltage landscape is changing the most rapidly and where those contour lines are the tightest. And so this is where the E field is the strongest. And that's kind of how we do it. A couple of rules about the relationship there. One is that the E field lines are always perpendicular to the contour lines, which have another name, the lines of equipotential. And so you might see both of those. Okay. All right. So I think we're ready to go. So in that case, by the way, let's go back over here and just show you the electric field would be pointed in the direction of steepest descent, and it's perpendicular to the contour lines from which it originates. So it's important to make sure that that's perpendicular there. So again, E field points in the direction of steepest descent. Okay. Right? Okay, all right, so one quick example just to bring this all together. So let's say that I have a couple of contour lines here. I'm making this up. I don't know, 100 volts, whatever, 50 volts, 0 volts. And I'll bring these lines close together. Negative 50 volts, negative 100 volts, negative 150 volts. Here's point A, here's point B. The separation here is 0.2 meters. 0.2 meters. The separation here, we'll say is half that, 0.1 meters and 0.1 meters. The question is, what is the strength and the direction of the E field at points A and B? And so we're going to use that formula that we had above here. So we're going to say that E is equal to delta V divided by delta X. And so what I'm going to do is I'm going to look at point A here. We'll just take care of point A first. We have to do both. Here's point A, and I'm going to estimate the slope here. So I'm just going to take a point on contour lines on either side of point A. I'm going to only go out one contour line because I want to have a very nice clean measurement of that slope there. I'm going to look for how much the voltage changed between these contour lines here. Starts out at 0 volts and ends at 100 volts. I'm going to keep this a positive number, so I have 100 volts on top. That's the total change in voltage between the contour lines that I've selected. Now we want to know the distance between the contour lines that we've selected, and that looks like it's a total of 0.4 meters. And so if I throw that into my calculator, I get 250 volts per meter, and I have the strength at point E. What's the direction of the field? Well, it's perpendicular to these contour lines, and it's pointed in the direction of steepest descent. So the question is, where's the mountain and where's the valley here? I hope you can see that 100 volts, that's higher elevation than negative 150 volts down here. So here's the mountain up here. And so the electric field's going to be pointed away or down the mountain, and it's going to be pointed perpendicular to that line. There's a nice right angle there, and that's super important to remember. All right. So let's do, that was point A. Let's do point B here as practice. So what's the change in voltage over the change in position? Again, I'm going to choose the contour lines on either side of the point of interest to estimate the slope. Looks like we start at at negative 50 volts and end at 150 volts. That's a change of 100 volts. And again, I'm just keeping positive values. There's no such thing as a negative electric field. Now, what's the separation between the 2 points of interest in this physical space? 0.1 plus 0.1 is 0.2 meters, and so the total electric field strength is 500 volts per meter. And that checks out because 500 is stronger than 250, and at point B, you can see the contour lines are closer together over here, which means that the electric field lines should be larger. So what's the direction that the field's pointing? Again, this is all downhill here, so it's going to be pointed downhill. I'm going to be perpendicular to that line there. Okay, that's all that we have for the voltage side of this. We're going to switch over and do electrical circuits next. So thanks so much.